When we are back today, we're going to tackle the stretching free energy term uh, in our microphase separation. Let me turn off the, excuse me. Anyways, so when we are in the ordered state, i.e. when we're in our micelle, our situation looks a little bit like this. So we have our corona here, we have our homopolymer, or not homopolymer, our dye block here, then it's connected to our basically red. They're supposed to be 50-50. Ignore. So we have our core, we have our corona. Inside here, our chains can either be basically stretched or compressed. So we've talked about this in our microphase separation in lecture 3, and lecture 4, kind of the free energy term for stretching. So we've derived this previously here, and again, we assume that there's no enthalpy change when we stretch our chain. So we're not exposing any kind of new binding sites. Again, it's an assumption. We knew the example of field refractor where stretching can open up some new binding sites, but we're going to ignore no enthalpy change upon stretching our chains here. So in the case of our micelle, we're going to kind of assume the most general case possible, i.e. the blocks can either be in both the core and the corona can be stretched or compressed, depending on the situation that we're dealing with here. So if we kind of assume this most general case, we have 4 terms in our energy compression. So our RC, so the radius of our core. So actually, let's go back. We go back to RC and LC. Actually, we'll see that in a figure. Actually, let's go back to our RC and LC here. So we have the radius of the core. So core radius, so RC. The length of our corona radius is LC. So let's go ahead and we can derive it right here. Not derive it, but just to kind of remind ourselves. LC, RC. Right in that expression there. So just so we know what we're considering. So this is going to be here. This is our length of our corona. This is going to be the radius of our core. RC. All right, so that is our core radius. So let's look at the kind of terms here. So this is the radius of our core divided by our free energy term here, and here, and here, and here, and here. So this tells us actually some really interesting values in our expression here. So the first two terms, not forms, our first two terms correspond to elongation. So we're looking at how is our free energy going to change if our polymer is stretched. So we know that if we stretch our polymers, our delta S of conformation, what happens to them? It decreases. And thus, our free energy, delta G, will increase. We don't want to lose conformational entropy. So if we're stretching, this value becomes large compared to, again, this n over 2 times b squared. Again, we're assuming 50-50, a equals b, which equals to b over 2, which equals to n over 2. That is the degree of polymerization of our, again, our dye block divided by 2. It is just going to be the number of those, monomer units times b squared. We're here again. You can replace this with a, but again, it's just the size. B is the monomer size. We're using the physicist chains model, but you could equivalently use a as well. Anyways, so if we're stretching, this term becomes large, and we increase our free energy. If these values are really large, these values will go basically to 0. And if we're in the stretching situation, those terms will. So these terms here are second two terms are compression of the same two regions. So again, unperturbed ideal length here versus the radius of our core. And so if these are, again, if we're compressed, if RC is small, RC is less than n to the half squared, right? B squared, then this term is going to explode. And this value is small, these two terms disappear. So again, you can see the beauty of this free energy term because it allows whether the core or the corona, whether it's compressed or elongated, we'll be able to capture it in this expression. So this is really, really nice. And again, unperturbed lengths based on each block being n over 2, 50-50. That's what we're dealing with again in this example or in this kind of formulation. So we would basically, you're going to see that there's only two terms are going to appear, either compression or elongation for the core or corona respectively. But we don't know, again, whether it's going to be stretched or compressed without doing the full free energy derivation. So the good thing about this derivation, it's already per polymer. So we don't need to kind of worry about any prefactor or the number of polymers in the micelle. So in the next video, we are going to tackle the mixing free energy of the free homopolymer and the polymer, our die block in the, between our die block in the corona and our free homopolymer. So I'll see you all in the next video. Thanks.